Lecture 3.3, RMS speeds and the Maxwell Boltzmann speed distribution. They typically call it the velocity distribution, but we don't include direction. So I'm going to say the speed distribution. Or a monatomic gas, one can calculate, and I got to be careful here. Note that I said monotonic gas. One can calculate RMS of a single gas particle. It doesn't have to be monotonic, but that's a lot of the times, because of the way we derive it, that's what it is. But what it really is, it's KRMS, which is the same as a translational. That's separate from K rotational and K vibrational. And this is clearly given by VRMS squared. And then I could either write this as 3/2 KBT, or I can write this as 3/2 nRT. So what you're seeing here is that this guy is per molecule, just like we wrote before, and this guy is per mole. Now, if I go and I solve for VRMS, I get the following relationship. I get that VRMS is then going to be the mass of the molecule. And because we're talking about molecules, it has to include 3 kBt. And then there's a square root. If I'm talking about the number of moles, then I have to deal with the molar mass times 3 RT. So these guys give you that value. Now, here's the most important part. The Maxwell Boltzmann speed distribution, remember, it's typically called velocity, but we're not talking about the velocity because that's a vector quantity. We're talking about the speed. So its distribution function is a probability function of the speed of a gas or a given temperature. So if you look at the probability function, so this is the probability per, let me be careful, it's not volume, it's speed. This is some function of dV. I could have just written PV. And what you'll find here is that you get this complicated relationship. Do I really need to talk about the details? Not really. I could have written the whole thing, but it really comes down to this. It's proportional to V squared, E to some constant, the exponential times minus a V squared dV. That's the probability function. Now, its importance is in interpreting its plot. Now, I'm going to give you a simple plot, which looks like this. And what you're seeing here is that you're seeing the probability of velocity versus velocity. And you can see here is that there's a distribution for 100K, 300K, and 1,000K. But the most beautiful curve, the sexy curve of all of this, is this guy right here. And I got this off of techscience.com. This is a gorgeous curve. It's absolutely stunning. And so I want to interpret the shape of this curve right here. Okay? I want to interpret the shape of this curve. But this is the one you want to think about, the one on the right, because it's done so well. So let's interpret this thing. So let's do an interpretation of what we just saw. I would say that the first thing that you should pay attention is that the shape of the curve. So what's special about the shape of the curve? So if I look at this guy, here's what I'm seeing here. Now, of course, I am not going to draw them as nice as this. But if you were to look at this curve, it has a peak, and then from the peak, it has a long tail. And this is what I'm plotting. So there's a couple of things that you should really pay attention to. The first thing is that the peak here, that represents the most probable speed. The problem is I can't separate speed from energy, so I got to say both at the same time. But remember what we said before. So if that's the most probable, the RMS value is always higher. So then this guy gives us the RMS speed. That's our average speed. Now there's something really special here, and it's in the tail end. This guy here is what we call the activation energy. And I'll explain this a little bit, more later, but what you're seeing here is that this tail plays a huge role. It's effectively they have enough energy to escape the surface of any gas. And we'll talk about that in terms of the atmosphere. So now let's discuss the general shape. How do you spell shape? I think this is it. So what I'm going to look at is that I'm going to look at higher temperatures of a gas. And what you're seeing here is that let's look at the left curve. This is 100K, this is 1,000K. There's a radical difference between the two. So the first thing that you should be looking at is note that the peak for higher temperatures is lower and shifts to the right. So if I say lower, what that really means is that there's a bigger spread in numerical values, which is what I should say now. The curve, I'm not really sure what I said before. The curve, I guess, spreads out more with a greater fraction of the gas particles have higher speeds than VRMS. So what you're going to find here is the speed of the activation limit is typically much, much bigger than VRMS. That's what that curve is really telling us. So now let's look at a little bit more of the details. So what did I call this? I called this 1. Okay, let's talk about 2. For a given temperature, we want to look at the distribution of the curves. So let's look at the 100K distribution. Look at the 100K distribution. See how it's very localized? So if you were to look at the tail here for the activation energy is really small. So that's what I got to reflect here. So then it says here, this is considered a low temperature. 100K is, even liquid nitrogen is higher in temperature. So this is a really low temperature. And what you'll find here is that there's a small spread in speeds. And the reason why there's a very small spread in speeds here is that it's very, maybe for a lack of a better word, it's localized speed value. So the most probable and the RMS are very, very close together. But now look at the 1,000K. And what you're seeing here is that when you look at their activation, it's way larger. So if I come in here and I look at this, this is a 1,000K distribution. So this happens to be a high temperature. And because it's a high temperature, you're going to find that there's a large spread in speeds. So that means here is that we have a wide spread in speed values. And they can be quite significant here. So the last thing that I want to talk about here is that I want to talk about this. Is that if you look, well, let me write things before I start bringing in graphs. At a given temperature, all gas particles must have the same, look at that, same KRMS. Why? Because it's proportional to the temperature. So if they have the same temperature, they have to have the same KRS. So if you look at room temperature, and I'm picking room temperature because that's what I'm going to focus on, I'm going to show you this curve here. Look at this curve. So if I look at this curve, let's see if I got the right curve. Yeah, this is my curve right here. So I'm going to make this a little bit smaller. So here's my curve. So at room temperature, that means that the microkinetic energy of helium must be the same kinetic energy of xenon. But they have different RMS speeds. They have the same kinetic energy, but they have different speeds. So let's focus on helium. So if I look at helium, which is 4 helium, well, that turns out to be a really small mass compared to xenon. And this, therefore, that has to have a higher velocity. So let's go highlight this. Right? So this guy right here, this is helium-4. And you could see that because it has a high RMS speed, it really, the curve is lower and spreads out. So there's a wide variety of speeds here. Now, if I compare this to xenon, this is 132 xenon, and you could see here is that its mass is quite large. So in order to have the same kinetic energy, its RMS speed must be really small. In other words, what this is telling me here is that the speed of helium turns out to be much larger than the speed. So check this out. So if I look at this, this means here it has a lower peak. So therefore it has more spread out V values. This guy, because it has a higher peak, that means it has less spread out of V values. So if I look at this guy, you can see here is that this is xenon right here. So you could see that this curve here is very, right? This curve right here is very localized. Very localized. That's the trend of the curve here. So now let's go look at, let me show you what I mean by all of this. So as an example, let me move this here. Here I go. Let's think about an example that we calculate these values here. So let's calculate the RMS speed of helium-2 and nitrogen-2 at room temperature. So when I think about room temperature, the standard temperature is 20 degrees Celsius, which means that this is 293 Kelvin. And it turns out that there are 2 ways to calculate this. So the first one, I'm going to use the molar form for hydrogen. So let's look at the molar form for hydrogen. So the molar mass of hydrogen, well, let's look at it. So I have, let me see, I think I just copied it. There it is. There's the molar mass. And we can see here's our molar mass. The molar mass is 1.01 to 3 sig figs grams per mole. That immediately tells me that the molar mass of H2 has to be 2 of these grams per mole. If I convert that into kilograms, then this is going to be 2.02 times 10 to the 3 kilograms per mole. That's our molar mass. So now if I go calculate the RMS of hydrogen 2, then it has to be the molar mass of hydrogen 2 divided by into 3RT. Remember, I said this was at room temperature, so this is going to be 3 times 8.31, and this will be joules, mole, Kelvin, times room temperature, which is 293 K, and then I'm going to divide, this will be 2.02 times 10 to the minus 3 kilograms per mole, and then I'm going to take the square root of this. So when I do that, here's what I get. I get that the RMS of hydrogen 2 is 1906 meters per second. That's 4 sig figs. I should have kept it lower to 3 because that's what I was doing. And this is approximately about 4250 miles per hour. So this is my hydrogen speed at room temperature. So if a hydrogen molecule hits you, it's traveling just a bit over 4,000 miles an hour. Now, the other form that we want to talk about is that we want to look at the molecular form for nitrogen. Nitrogen gas is special because almost 80% of the air is nitrogen. So here we go. So now, so if I look at nitrogen on the periodic table, here's what we see. What we see here is this. Now, if you look at the atomic mass, which is this guy, what this does here is that this is the number of nucleons, which means it's the number of protons plus neutrons. So there's 14 protons and neutrons inside that nucleus. So here we go. So then the number of protons or neutrons inside the nucleus reads like this. So here's the mass of nitrogen. So then I have the mass of the nucleus plus the mass of the electrons. So let's look at the numbers here. For starters here, the mass of the proton and the mass of the neutron is much, much bigger than the mass of the electron. In fact, one proton is around 1,800 masses of the electron. So what we can do here is that we just ignore the mass of the electron. It's so tiny. We don't have the sig figs. Another thing, one of the miracles of the nucleus is the mass of the proton is very close to the mass of the neutron. So if I have 14 neutrons and protons, I can treat them as 14 protons. So now if I look at the mass of the proton, it turns out to be 1.67 times 10 to the minus 27 kilograms. So if I put this out, then here's what I have. I have nitrogen. So if I have nitrogen, then I'm going to have 14 masses of the proton, which means then, 14, which then means this is going to be 14 times 1.67 times 10 to the minus 27 kilograms, which then means that this is going to be 14 times that. That's roughly around 24. It's not 24. It turns out to be 23.4 times 10 to the minus 27 kilograms. That's the mass of one neutron. So here we go. Let's calculate it. So the RMS speed of nitrogen gas at room temperature is then going to be V RMS. Now look at this. It's nitrogen gas. So it's 2. So that has to be the mass of N2. And then this is going to be 3 kBT. And then I got to take the square root. So let's put in the numbers. So here I go. So this is going to be 3 times the Boltzmann constant, which is 10 to the minus 23, which is the joules per Kelvin. And then the room temperature is 239 K. And then the mass of nitrogen is 46.8. Remember, I got to multiply by 2. Maybe I should just write this out instead of just multiply in my head. So this is going to be 2 times 23.4 times 10 to the minus 27 kilograms. And then I got to take the whole square root of this. This turns out to be 511 meters per second. And if I round that, that's around 1150 miles per hour. And this is the VRMS of nitrogen gas. You know, by the way, why should I even care about nitrogen gas? Well, 78% of the atmosphere is nitrogen gas. It's inert. You breathe it in and you effectively breathe, and you breathe it out. The only thing that you take in is oxygen, which is 21%. Who cares about nitrogen, right? Well, the atmosphere is a mixture of nitrogen and oxygen. Of course, there's trace amounts of other gases. So it's a mixture of gases that surrounds the Earth. But guess what? It helps make life possible by providing us with air to breathe. It shields us from the harmful ultraviolet radiation that comes from the sun. Furthermore, it's trapping heat to warm the Earth and preventing extreme temperature differences between day and night. There's a good reason why nitrogen is important. Okay, I probably shouldn't have said that, but here we go. So what I want to do here is that what's the physics behind these calculated RMS speeds. I did not choose these by random. And here's the answer. H2 hydrogen gas is the most, how do I say this? Plentiful? I guess that's a good word. Plentiful element in the universe. And if you look up the numbers, it turns out that 75% of the universe is hydrogen. And yet, our atmosphere is primarily nitrogen gas, which is 78%, and oxygen gas, which is 21%. The other stuff is trace amounts. Hydrogen 2 gas is only trace amounts in our atmosphere. And the question, of course, is why? Why is that there's so much hydrogen in the universe, but we're effectively devoid of hydrogen in our atmosphere? So here's what we find. It's believed that there was plenty of hydrogen gas in the early part of Earth's, what do I call it? Earth's evolution. The Maxwell Boltzmann curve tells us why there is effectively no hydrogen 2 gas in our atmosphere. At least, let me be careful. Hydrogen gas in our atmosphere today, because at some point there is. So what I did here is I created this curve, which I modified from Wikipedia, and it looks like this. So here's what we know. So at atmospheric temperature, we calculated that value for 20 degrees C. And you can see here that there's the peak value, which is the most probable, but look at the RMS. We just calculated that. It's off the peak value, but close. That's 1906 meters per second. But then there's this activation curve right here. And it's this activation curve that's really, really important. So the question is, why is it important? For starters here, we could say that the tail end of the curve represents the fastest H2 molecules whose speeds exceed Earth's escape speed. Most people say velocity of 1100 meters per second. So if you exceed 1100 meters per second, I'll stop right here. You escape. So then here's the most beautiful part. So similar to adiabatic cooling, so for example, if you take a spray can of hairspray or deodorant, as soon as you spray it, it's cooler. So similar to adiabatic cooling, when H2 gas escapes, the Earth's atmosphere cools a bit from the sun's and Earth's warmth. We're really talking about radiation here. It reheats the atmosphere and I guess this is the way you spell reestablish, reestablishes the Maxwell Boltzmann curve. But it's more complicated. So let me take the same curve that I just did. So here's what happens. Now note, so I'm going to lie a little bit. This is what we call a little bit of a white lie. So if particles escape, what actually happens? Well, there's less particles. So what am I going to do? I'm going to draw a different curve. So what you're seeing is that as the escape, you could imagine that, oh, that's not a good curve. So it comes here and it's gotta end at the same spot. You can see here is that the curve is decreasing and it continues to decrease. So what you're seeing here is that the curve is decreasing to nothing. Now, I gotta be careful with that language. The curve has the same shape. But what you're seeing here is that you're seeing this exhalation tail. So as the Earth rewarms the atmosphere, there's always going to be a tail that gives you that activation. And it's that activation that causes these particles to exceed the escape velocity of the Earth. So what I'm really saying here is that, again, this is not correct, but this is a conceptual thing. I would then say the curve gets more shallow. It doesn't, because there is less hydrogen gas in the atmosphere. The probability stays the same, but they keep escaping. And as a consequence, the process then repeats again and again until there are only trace amounts of hydrogen 2 gas in our atmosphere.